Thank you very much for coming. I'm a fourth-year PhD student working with Professor Janusz Bialik and Professor David Pozo. And today I would like to share with you my experience of using cooperative game theory in research and hopefully to motivate you to use it in your own studies. And this lecture is an introduction lecture. I will introduce some basic solution concepts and basic examples, so I hope you enjoy it. And first, few words about myself. I graduated from Moscow Power Engineering Institute, and as you may see from my master's and bachelor's theses, I studied pure electrical engineering, power system design, power quality management, operation and control. And also in the last 2 years of my education, I participated in an exciting project. We were developing a 3D substation training simulator. It was an interesting experience. We traveled to real substations in Belgorod Energo. We filmed all the operations and then reconstructed them in 3D and also modeled a brain of this simulator. So you should be operating breakers and transformers and the power flow every time it is recalculated. And this simulator is still available at MPI, and you may see here even Professor David enjoy it. So if you're interested, approach me and I can tell you the name of professor and you can visit this simulator. And in 2016, I joined Skoltech and I completely changed my topic. I started studying power markets, mathematical optimization, transmission expansion planning, and in particular, cross-border cooperation. And during my first year, I had a chance to undergo an internship in United Nations in Bangkok and also participate in the United Nations conference in Irkutsk. And after that, I realized that there is a strong political and economic interest in cross-border electricity trade. And therefore, we started running transmission expansion planning for some cases, for example, for the Asian supergrid case. And also, I was invited to the symposium on Asia International Grid Connections in Tokyo. And after that, we finally decided that this will be the topic of my thesis. But the question arose, what new can we do here? How to bring scientific novelty? And after several discussions, we realized that there is a need to use cooperative game theory in order to allocate the investment costs of such projects among the countries. Because before this, the usual question was how to optimize the interconnections, how to make this cooperation optimal, but very few papers addressed the issues of cost allocation. And also I want to highlight that there are many projects of power interconnections in the world, especially in Europe and in North America. And one of the greatest organizations that exists so far is called Global Energy Interconnection Development and Cooperation Organization, that is created by Chinese State Grid Corporation, and they are developing huge plans like cross-continental power interconnections. And by the way, I think that we still have several copies of this book by Liu Zhenya, and if you're interested, you can approach me or David, and we will share it with you, but it is in Russian. So, as I said, we understand... In Skoltech, we have it in Russian, only in Russian.
Is it translated or it's written in Russian?
No, it is translated to Russian, and Chinese company granted it to us.
Okay.
But you can find an English copy in the internet, I think. So, yes, after this preliminary research, we realized that there is a need for cost allocation techniques. And also, as you may see, 3 years ago, I knew nothing about cooperative game theory. I had to start from scratch. And therefore, today, I want to show you how my research evolved and motivate you to use the same techniques in your studies. So let's start with my favorite example, one of the simplest ones, that is called the gloves example. And I would ask you to imagine that you are the left person that has the left glove, and this glove is not of such a good quality. And you know that you can go to a market and sell it for $1. But you have another person that has the right glove that is somewhat better, and you know that, and he knows that he can sell it at least for $2. But if these people cooperate and they make a pair of gloves, they together can get $10. So this is an example of mutually beneficial cooperation. And the only issue is how they should split the $10 among themselves. And this is the question that I want to ask you. And in order to help you, I drew here this empty ruler. And you may see the points like 0, 10. This means that you get $0, another player gets $10, the half division, and 10 zeros. So do you have any ideas how you can split the $10?
The obvious answer is proportional.
Proportional to initial cost?
Yes.
It is, I would say, semi-correct, because it is possible to do, but what if one glove will cost very close to zero? Then the proportion will be huge, and this could lead to some strange results. And in order to give you some ideas, let's consider, is it possible to find a solution here, like $10 zero at this point, at the end of the ruler?
No. Somewhat unrelated question. Did you ask this question to Yura Dvorkin?
This exact no.
Just try to do
But I remember
Sorry for I just can't resist to ask this question.
I remember at Inform's conference I was talking about this, and Yuri passed by and he looked, and then he just continued walking. So probably he didn't like.
Oh no, just he wouldn't miss that.
Okay, so if we consider a point $10 to one person, zero to another, this is an infeasible point because it's not rational. The player can get $2 on his own. And by this simple logic, we can understand one of the basic cooperative game theory concepts that is called the core of the game. And we can plot it on this ruler, the green space, the feasible solutions to this problem. And through this lecture, I want to show you that even though cooperative game theory may seem a bit complicated, it is based on very simple, intuitive concepts that you can realize in a few months, maybe. And okay, how can we solve this problem mathematically? And the answer here is that we need to describe all possible coalitions. And I will give several simple definitions here. The main concept is that we need to describe two things. First is a set of players and set of coalitions, what coalitions we have and what players belong to them. This is like a combination of possible scenarios. And the second is the so-called characteristic function, nu, that describes each of the possible coalitions. And once we describe this, we can also formulate this rationality concept that is two basic conditions. And the first one is called a coalitional rationality. This means that each coalition cannot get less than it gets on its own. And this is what we see. If you have $1 for your left glove, you will not agree to get less. And the global rationality constraint means that the gain of all of the grand coalition should be equal to the payoffs of this coalition. So we keep these allocations equal to the total gain that we get. And let's see how this works for this simple example. First of all, let's calculate the number of scenarios. There are two players, so 2 to the power of 2 minus 1 is 3 possible scenarios. And we can mathematically formulate the core constraints. And you see that this is payoff for player A is greater than 1, player A plus B is 10, and B is greater than 2. And you see that this is pretty simple and easily programmable. And moreover, the core is formed of these hyperplanes, and therefore it is a compact convex set. And you can perform any additional optimization or any additional techniques within this set. And also I drew this table for you when you see what are the coalitions, the 3 possible coalitions, and the characteristic function. And the next question that you may ask, but how to get a particular solution for the problem? And the answer is that there is no single solution. There are many solution concepts, and the most famous one are the Shapley value, the nucleolus, and the kernel. And let me introduce the Shapley value that probably you heard about. The formula may seem complicated to you, but first let's talk about this right component. And this is called the marginal contribution of a player to a coalition. This is the difference between what coalition gets with the player and minus what coalition gets without the player. So this is like a margin of what player brings to a coalition. And in order to better explain you this concept of marginal contributions, I heard a rather funny example. You may imagine that there is a room and several men entering it. And the goal is to lift something heavy. And let's see what are the marginal contributions. If the first man comes, he tries to lift a heavy weight and he achieves nothing, like 0 result. And then more and more men are coming, and finally the last man helps and they lift this heavy weight up. And if we consider marginal contributions, they will be like 0, 0, some small contributions, and a huge contribution. So this very smart formula by Shapley, it says that we need to consider all possible contributions, all players to coalitions, in all possible orders. So we need to consider how the men can enter the room in different orders and lift this up, and then to allocate this gain, to analyze the effectiveness of each man. And we can do this for the 2 gloves example, and this is rather easy. We can calculate it here manually because there are only 2 scenarios. They cooperate or they do not. And we see that this is coalition of player 1 with the left glove minus 0 because there is no cooperation at all, and the grand coalition minus the grand coalition without player 1. And in this fashion, we get this interesting result, 4 and a 5 and 5 and a 5. And this is right in the middle of this bargaining range. And this makes sense to me because you see that players in this cooperation, they have equal bargaining power, equal influence. Both of them can break the agreement. And therefore, this surplus is divided by half. And yes?
So it's somewhat counterintuitive because the ratio of these costs is not 2 to 1, yeah? As you would imagine. So sometimes you can think, okay, yeah, you should divide this 10 by like 2/3 goes to the right and 1/3 to the left, according to the ratio.
This is the ratio. This is not the ratio approach. Yeah. And you see an interesting fact that the difference between the left and the right glove was $1. And this difference preserves here. So
because it's in the middle.
But this is a simple example, and therefore we get such a simple solution. And Shapley value is often referred as the efficient and fair cost allocation.
But just,
yes.
Sorry, just one question, because it could be related to practice. Suppose you have not such a good glove in the right-hand part. Suppose you have a glove that, for example, costs $1.
Yes.
And you're about to make a decision on investment in its repair.
Yes.
So that it costs more on its own. But then when you plan that you're going to have a coalition, maybe you won't make this decision on investments in repair. In other words, it's related to power systems, because you can measure these shares of different participants in terms of, I don't know, complexity of their infrastructure. And then when they combine together, if they plan that ahead, they might affect severely their decision, investment decisions.
Therefore, we assume perfect information. If not perfect information, then the players could cheat. They could say, my glove is infinitely good.
Okay.
Okay, and this is the simple example. And because of these properties and this account of marginal contributions, the Shapley value is often called as the fair allocation concept, and it is used to measure players' bargaining power. And let's see the similar example, but in power systems. Imagine that there are 2 nodes with certain demand and generation, and we can set the generation cost functions, and you may notice that cost function at power system B is higher. We can plot this and see that indeed the generation cost, this red area in system B, is much higher. And this blue area is called the revenue of generation companies, so we can call this the social welfare. And if the countries agree to build a line, let's say 400 megawatts, we can see how the situation changed. There is now a power export from system A towards system B, and the overall generation cost decreased. And also from the mathematical point of view, this problem is similar to power flow optimization or transmission expansion planning, where in the objective function we see the minimization of generation costs and investment costs. But in this simple example, I created not a constant generation cost, but linear functions, and therefore the cost itself is an integral under the function, and it is a quadratic function. And therefore, in these pictures, you may see that it is a quadratic optimization. And this is the power generated by the expensive generators in power system B, in power system A, and the initial point 1 when there is no cooperation. And this is the 3D figure, so once we build more capacity, this space evolves here, and we are going right to the point 2, the least cost point for the system. We can go even further to point 3, but it's impossible because there is a restriction on power capacity. And if you consider...
You mean the restriction on the flow?
Yes, we say 400 megawatts maximum, and they achieve this. So point 2 is the feasible optimal point. And coming back to cooperation, we see the same problem. There are two players, system A and system B. They had some costs before and some costs together that is decreased. We again can calculate this simple Shapley and again see the generation cost allocation by the Shapley. And even though these values can tell you not so much, you may compare them with the initial costs, like separate costs of no cooperation, and you may see that the savings are allocated equally again. And this is the fair solution for the problem. And yes, as I said, I started studying cooperative game theory principles from scratch, and I want to share with you just some ideas how you can also understand this. First of all, I watched a course on Coursera, Introduction to Game Theory by Matthew Jackson. It was very useful and encouraging. And once you understand basic concepts, I recommend you this famous book by Michael Maschler about the game theory, and it describes both non-cooperative and cooperative game theory concepts. And about electricity markets, operation and economics, I think most of you know this famous book that Janusz likes, Fundamentals of Power System Economics. And I hope that you're ready for more complicated examples once we introduce more players. And here I prepared for you the dinner example. And imagine there are three friends. I put just some random names like Arman, Andrey, and Tatiana. And they discuss going to have a dinner, but for some reason they want to discuss this in details. And they figured out that if they go together, they will buy big pizza, cola, and big fries. And the question is how they should pay for this. And in real life, this question may be a bit stupid. They can pay in equal shares, or maybe one of the friends can say that I pay for all of you. But imagine that this is not a pizza, but a multi-billion dollar project. And this level of inaccuracy is unacceptable in such projects. So you need some justified solution for investment cost allocation. And therefore, we go to cooperative game theory. And the theory tells us that you need to consider all possible scenarios of cooperation. And first of all, we ask people, what are you going to do if you do not cooperate today? And we see that the players are in different conditions. For example, Arman is a bit hungry, and he says, I am going to buy half pizza, cola, and fries, and this cost me $16. Andrei is also a bit hungry, but Tatiana, for example, says, I'm just going with you for the dinner, but I'm not hungry. I want just small fries. So we see they are in different initial conditions. But also, since there are three players, we need to consider most scenarios of their mutual cooperation. What happens if Andrei goes with Arman, but not with Tatiana? What happens if Arman goes with Tatiana? And maybe just for fun, we can create a situation where Tatiana and Andrei, for some reason, do not cooperate at all. They will not go for the dinner. And let's see what happens with this game mathematically. We can create this table. And 2 to the power of 3 minus 1 leads to 7 possible scenarios of cooperation. And you may see all the 7 coalitions here and the characteristic function. And based on this characteristic function, we can use the Shapley value formula and evaluate how the costs should be allocated among the players. And this is the Shapley value allocation, and it is meaningful. You see that Arman indeed pays more than half of the meal because he was hungry and he wanted more. And Tatiana pays a little share of this because she was in good initial conditions. She didn't want to eat at all. And also, we can compare not just a cost, but the difference between the new cost and the initial conditions and see the savings allocation. And the situation here is a bit different. The players are more equal, but still Arman has the better savings allocation, and this means that he has a better bargaining power in this example. He is a more influential player, while Tatiana has not so much money to invest in this, and she's not such an influential player. And this is just a...
If you consider the savings as a ratio of the contribution, the situation is quite different. So Tatiana now saves the most because she's about to invest 3 and she saves half.
If you say in percentage.
Yeah. As percentage, her savings is much better, and it's the same in the other examples as well, I guess.
Maybe, but if we consider like in global shares, we see that Arman gets more in dollars, in terms of dollars.
Yeah.
And this is just as I said, the most common solutions, and there is much more in cooperative game theory, and I don't have time to explain everything, but just to give you some ideas, we can further evaluate the solution that we got. For example, we can measure the so-called excess of a coalition. And the excess is the difference between what a coalition gets on its own minus what it is allocated. And therefore, I created here an additional column summarizing the sum of allocations for each of the coalition and the excess. You may notice that for the Grand Coalition, the excess is 0 because 3 players are 3 players. There is no difference. And for other coalitions, there are some excesses, and you may see that Tatiana is the less satisfied player because, as you said, in percentage, maybe she got a lot, but in terms of dollars, she invests not so much, and she has not so much surplus. And please notice that the most satisfied coalition is this coalition with the excess 4, Andrey, Tatiana, because, yes?
But you also do not consider that if 2 of them play together, they gain something. So
Yes, I consider this.
Yeah, coalition.
Yeah, so you don't form a coalition of 2. In other words, the cost for 2 is just the sum of their separate costs.
No,
So
No, I created a game, not a sum. You may notice that this is this is not a sum. I created.
I see.
This is called a super additive game when
okay.
each coalition is better than no
Yeah,
cooperation.
I didn't notice that. Okay.
And yes, we can measure the excess. And this coalition, Tatiana Andrei, is the most satisfied one. Why? Because without the Grand Coalition, they do not cooperate at all. And once they enter the coalition with Arman, they get some surplus, and therefore, this turns out to be the most satisfied coalition. And as I said, there are much more solution concepts. Maybe I will cover more details in the next lecture. And based on this idea of excess, there is a solution concept called nucleolus, and it is a series of linear optimization problems that tries to minimize the dissatisfaction of coalitions. And this leads to rather interesting results. And the last example for today is the same 3 players, but in power systems. Once again, imagine 3 power systems that are going to interconnect. And I created different cost functions here, but still system B is the most expensive one, and it has the highest power demand. And in order to solve this game, we need to launch the optimization model several times. So this is the same cost minimization model of generation cost and investment cost, and we launch it for multiple scenarios. So let's see, this is scenario number 1. I call this no cooperation. This is the generation cost. There are no lines, no investment cost, and the total cost. And then we start running optimization models. We calculate scenario of the Grand Coalition. You see that all the lines are built up to the maximum of 100 megawatts. Then we consider scenario AB. You see only this line exists, AC and BC. So we composed a characteristic function, and we can implement the solution concepts. I show them in the table in terms of cost allocation and cost savings, so the Shapley value, the nucleolus, and equal sharing. And more interestingly, there is a way of plotting this using this barycentric coordinate system. And in order to give you an idea what is barycentric coordinate system, you may consider point B. And this is the point where system B gets 100% of savings. And the further we move away from point B, system B gets less and less savings. This means that here, system B gets 0 savings. And this is an interesting way of showing the possible allocation solutions. And this region inside is called the core of the game. As I said, the convex set formed by half spaces, and some interesting solutions. For example, right in the center of mass of this triangle, we have the equal sharing point, one of the most obvious solutions. And Shapley value and nucleolus, they're rather close for this case, but we see that nucleolus sees that probably player A is a bit underestimated by the Shapley value, so the allocation solution moves a bit towards system A. And this approach has been implemented many times. I found several papers, started from a famous paper by Dermot Gately in 1974 and some modern research about interconnections in the North Sea and interconnections among Brazil and its neighboring countries. And just to show you some of the research, this is the famous paper by Dermot Gately. And I think it is amazing that this research was done more than 40 years ago. Without computers, he plotted such a nice graphs, also visualizing possible allocation solutions. He considered 3 power systems in India as a case study, and he considered many solution concepts. The Shapley, the nucleolus, he also suggested his own solution concept that he called propensity to disrupt. And then the next influential study that I know is the study by Javier Contreras in 1999. By the way, this is the supervisor of Professor David Pozo. And he also considered possible cost allocations and coalitional formation in power systems. And as you may see here, he used a backwards induction to consider how the grand coalition formed and the whole history of formation, and used this to allocate the costs among the power systems. And there are much more papers. Just to give you an example, there is a paper not about power system, but about so-called horizontal cooperation. And Lazana here explained how horizontal means more or less equal firms at the same level of operation can cooperate to get some synergy. And he explained this on the basis of logistic costs for shipping, how the shipping companies may cooperate to get less cost. And also you may see that he analyzed the core and different solution allocations, and he concluded that this could be implemented in many applied topics. So yes, I think that's all for today, and I want to tell you that this is not the only way to implement cooperative game theory in power systems. I saw papers about cooperation of microgrids when they agree of building some equipment or following some rules, and then they share the allocations, or cooperation in CO2 emissions reduction. So there are multiple ways when you can think about how to implement cooperative game theory, and it will give you some insights about players' position in this cooperation and possible ways of transferring money and so on. So I hope you enjoyed this lecture, and thank you for your attention. Yes.
Can you show the slide with WD geometric representation? Yes, this slide. And this point where Shapley nucleus and equal sharing is this point, does this point correspond in some geometrical or physical property of triangle?
Yes, a center of mass is equally distant from, right?
Center of mass.
Equal sharing point is the center of mass. Yes, and therefore,
this center of mass.
yes.
And below.
And below,
These points.
there are some interpretations, but they involve game theory. But basically, there are some sets, and you try to find a weighted average of this set. This is called the Weber set, if I'm not mistaken. This is similar to the core, but it's a bit larger. So you find some weighted sum of contributions, yes, like Shapley value does, and you find these final points. And you can plot this as you saw even in 3D.
Yeah. Also, nucleolus have some correspondence with the core, right?
Yes, nucleolus. It is proven. There are many theorems in game theory, and for example, it's proven that if the core exists, nucleolus is always the part of the core, so it's somewhere in the middle.
You mentioned barycentric coordinates. What cells they are applied here? So if you consider like equal, then the mass at each point A, B, and C is the same, and then your XE is the center. But what if? So you have different combinations when the masses associated to points A, B, C, and C are different, right?
If players are in equal conditions, initial conditions, you will see that there will be the core like a triangle somewhere, like perfectly centered. But you see that this feasible space shifted towards system B and A, and this represents the inequality. That this figure, like triangle itself, stays the same, but the core and the solution moves inside. And if some system is more influential, probably the allocation will move towards it. It will get more. So the point and the core moves, but the figure stays the same. It can enlarge or shrink. If you allow to build more lines, the whole triangle, this space can just expand. Or if you forbid the lines, there will be zero space, like no cooperation.
one question. Can you go back to the figure with the areas, red and blue, that you have between only two areas, 400 megawatt interconnection? That one. So basically, when they interconnect, I mean, you solve an optimization problem and you derive what is basically the direction of the flow and the total cost of the system.
Yes.
Right? And you also have, like, let's say, a cost for the area A and the cost for the area B, right?
Yes.
And those costs are going to be, let's say, different than the ones if they are integrated. Okay. What is the, let's say, the motivation of the area that is reducing the cost of using the Shapley value to calculate a new cost allocation then?
Okay, so the initial cost of area A was really low, and then it starts exporting power, and basically it suffers because it needs to generate more. So it needs to be compensated somehow. And in this example, it's seen that there is enough savings, enough money on the table to compensate it, because the sum of generation costs here is larger than sum of generation costs in the interconnection scenario. And the question is, how much should system B pay to system A? And this can be calculated based on the Shapley value, that we get these allocations and we know that system A should end up in this point, in having this cost. And therefore we can calculate, okay, how much should be transferred. So this is one of the ideas how to calculate this compensation.
But does that diverge from the, if you go to the previous figure, that one, yeah. So I have a locational marginal price on A and on B, right? So basically, if I have the locational marginal price on A, I just multiply that by 400 and I would have how much B would pay. Yeah. Does that differ from the Shapley value?
No, this is derived from optimization and from energy economics. Yeah, you see the prices I also plotted here, they change. This price increase, this price, those prices decrease.
So are you saying that your solution will exactly correspond to the location or marginal prices?
No.
Because the location prices, the marginal prices, they will depend on whether the line is congested or not. So it's congested in your case, yeah?
Yes.
So we will have some
there is still a difference.
Yeah, of course. You will have some solution, and it's not the solution that you just presented. It's different one.
Based on the locational marginal price theory, I can evaluate what would be the cost, the prices. Yeah. But if there is a need for compensation, we can turn our attention to cooperative game theory.
But you see, when you've got the locational marginal prices, you kind of calculate the compensations automatically, yeah? Don't you?
Not exactly, because there are many players, and generators here will be happy to export more power because the social welfare increase. But the consumers will suffer, and maybe they will not agree to cooperate. So there are multiple parties to be compensated.
Okay.
We look at Shapley formula. Can you show this? Yes. Shapley value, yes. And these conclusions are fair for deterministic case when we are strictly can strictly determine characteristic function nu of S.
Yes, for each collision.
These conclusions are conserved for case when nu of S have some uncertainty, for example, some noise.
I saw at least one paper when they said that what if we don't know what is the value of collision, we only have some probability, and it is much more complicated, and people did this, they put probabilities inside. It is possible, I didn't do this, but yeah, if you don't have any deterministic data, you can make it more hard. But yeah, this example is a static one, deterministic.
You mentioned fairness a couple of times, so how to measure how fair some solution is?
It is a hard question. There are many, how to say, many definitions of what fair solution should satisfy. And in this slide, I mentioned the efficiency, the symmetry, the null player, and there are much more theorems. And for example, efficiency means that the entire value is distributed fully. The symmetry means that if there are two players in exactly similar conditions, that they will get exactly similar, like equal payoffs. The null player is the rule that if player brings nothing, he will get nothing eventually at the end of the allocation procedure, and much more. And Shapley value satisfies a lot of these properties, and therefore it is said that it is more or less fair solution. While nucleolus can allocate something maybe to players who brings almost nothing, and some properties will be ruined. But this is not so obvious, even to me. Some of these definitions are not obvious.
I feel like the concept of fairness is related with a marginal value. So, like when you see when you have the option to cooperate, you can understand what will be the marginal value. And so, for example, if we are cooperating number 3, like the sample of the table was really nice, I think, because we can think like, well, two of us, we are trying to pull up the table, but we were not able. But then Peter came and then they pull up. So his marginal contribution actually was a lot. For us was 0, and with him was 1, right? So we pull up. But this is not fair to give him like all the credits.
Why not?
Because I was stronger than you. So then there is this concept of creating all these possible
Overseas.
yeah, all the possible combination how the cooperation can be generated. So we make the assumption, like Peter and myself, so we are trying to pull up the table, and then so this is another scenario. So all those scenarios that he was mentioning. So at the end, so you can see like there are a lot of possible combinations that actually create some benefits of value, this value function, and you have to compute what is this marginal value for every of this situation. And there is a monster there at the beginning of the Shapley value, but this is actually the proportion, or like what is the probability of having this scenario, right? Or the combination. So fairness actually is the Shapley value is the only allocation rule that gives you fairness. And this is nice because also I think you comment by pretty fast, like there is it gives you only a single solution, so you don't have more than one solution. So every time you will find just a single solution from.
But also according to this definition of fairness. So if you use some other definition of fairness, it will be different.
Yes. So fairness here is related with the margin value that anyone can contribute.
But can you then weigh the probabilities of having each realization? Because you consider every coalition as equally probable.
Yeah. So
you then can change the probabilities of certain coalitions and then get some other answer.
Yeah. For example, in our case, so the probability will be the same. Like with you and myself, so we are trying to pull, then it became both of you.
But it could be different, and then you can just write some weighting coefficients.
They could be different, yes. So if you see in the sum, so the first part, like this monster, so it's basically giving you this probability of this particular.
Yeah.
That's why there are factorials, because we consider all from combinatorics, all scenarios. So thank you. Next time I'm going to show the cases that we analyzed and the papers that we written. Hope to give more details and more sophisticated techniques.